Last time we saw this equation, which was that the calculation of the Laplace transform is an integral like the Fourier transform. But you just have a negative st up in the exponent. Okay? And this may converge or may not for some s. So there are two parts then to the Laplace transform. You have the region of convergence, which would just call the ROC. And then within that region, you have a formula. So that's x of s. Right, so you have these two parts, both important for expressing the Laplace transform. We saw, for example, let's recall the example we saw last time. And that is that if we take this function, e to the t u of t, and we do a Laplace transform of it, then we get 1 over s minus 1. And also if we took the function negative e to the t u of negative t, and we took the Laplace transform, we also got 1 over s minus 1. All right, so they both had the same Laplace transform. That's not a good thing. However, the difference was, well, let's first graph these to show. These are actually very different signals, right? We have one of them goes like this, and the other one goes like this. Right? So they're very different signals, but the Laplace transform expression is the same. And the difference between their Laplace transforms is exactly this region of convergence. So the ROC over here is the set of s's such that the real part of s is greater than 1. The ROC here, and I won't always write it using that set notation. I'll just say that it's the real part of s must be less than 1. So even though the formula for the Laplace transform was the same, the region of convergence being different is what made these, is how you identify these are two different signals. Because we will have an inverse from the Laplace transform, just like we did for the Fourier transform. Notice something else interesting here, that in this case, there is no Fourier transform. Why is that? Why do I say that? For this formula on the left. Yeah, exactly. Energy is infinite. You would notice that the integrals would not converge for this thing. So we wouldn't even be able to do anything spectrally, anything having to do with Fourier. But now what we've done is we've allowed ourselves to do something related to Fourier, and we'll review how this is related. Because so the Laplace transform can handle this. Over here, notice that the real part of s equals 0. That's a particular line, right? Where the real part of s equals 0. That's the imaginary axis in the s space. That is in the region of convergence. Okay. Now, that implies that the Fourier transform exists. Because if you recall, we related the Laplace transform to the Fourier transform, and if the real part of s is 0, it is exactly the Fourier transform. Okay, and we'll review that in a minute. So the Fourier transform of x of t in this second case, because it's in the region of convergence, that has a Fourier transform, and that Fourier transform is just x of s, as we've expressed above, evaluated at s equals I 2 pi f. Okay, so that means that's equal to let's go look at what x of s is. X of s right here, right? And you just plug in I 2 pi f, and that means that that is 1 over I 2 pi f minus 1. That's the Fourier transform of this thing. Okay, it just pops out of the Laplace transform. Okay, so let's talk about the inverse of the Laplace transform. How do you invert this thing to get back your signal? So first of all, if the imaginary axis is in the region of convergence, then what could you do? So in this case, maybe you can think of a method of getting the signal back. What? Well, the opposite direction of what you're saying. I'm assuming you have the Laplace transform expressed somehow. So you have some formula of s, and we want to get back to x of t. So do the opposite of what you said. Yes. Yeah, actually, it's just that simple that you just take the inverse Fourier transform of x, the Laplace transform that we're assuming you have, of I 2 pi f. So just plug in I 2 pi f in place of s. Now here I put a subscript L. The only reason I've done that here is because we have capital X representing, I use capital X for the Fourier transform, discrete time, continuous time, whatever. And now I'm using capital X for the Laplace transform. So usually it's not going to be confusing, but if it potentially is, I'll put a little L underneath that that's the Laplace transform I'm talking about here. So you take the Laplace transform, plug in I 2 pi f instead of s. That gives you a function of f. That should be the Fourier transform, so do the inverse. Okay, so there's one method. Of course, this only works if the Fourier transform existed, which would have meant that the imaginary axis was in the region of convergence. Okay, in general, do the following. So x of t is the limit as f goes to infinity 1 over I 2 pi integral of this type of thing. Okay. Of your Laplace transform times e to the st. So, in some ways, it's just like the inverse Fourier transform, but the weird thing here is x of s, the domain of this, is the complex plane. This is not a function of f. Okay, it's a function of complex numbers. So to do an integral, this is something many of you won't be familiar with. How do you integrate through a two-dimensional domain? And what this is saying is you just integrate along one line. You choose the line. Do this for any sigma, you'll get the same answer. So for any sigma in the region of convergence. So okay, so what we're saying is pick a sigma. Of course, that means that these numbers here, you're going from sigma minus something going to infinity in the imaginary part to sigma plus something an imaginary part going to infinity. So it's a vertical line in the complex plane. You're integrating along that line. And this term here is just because of the change of variables, ds versus df. You get this constant out front. Okay, but you do this now. Turns out we're not going to use this. See you guys. They're going to go color and play. Okay, so we're not actually going to use this. Okay, so I'm just telling you this for your information that yes, you can get x of t back. But we're not going to do this type of integral. And this actually opens up a nice discussion of, complex analysis, and some of you will study that or have studied that, in which case you talk about integrating through the complex plane and what it really is about. Okay? But it's interesting, from complex analysis, you would find that you would know why integrating on any line here would give the same answer. Okay? So you just pick a sigma and you go for it. Now, but I say we're not going to have to do this because we're only going to be looking at Laplace transform in some important special cases where Laplace transform table will be good enough. You don't need to go backwards. You just know enough of the forward Laplace transforms, and you just memorize. Actually, we only need to know about 2 Laplace transforms to do everything we want. Okay, so we're not going to find ourselves doing these integrals. Now, I'd like to explain, though, why such an inverse works. And to do that, let's go back to our interpretation we talked about last time of this Laplace transform. So remember that we said x of, if we take this Laplace transform evaluated at sigma plus I 2 pi f, all I've done here is just represent s as a real part, sigma an imaginary part, 2 pi f. Okay, I'm just giving variables for the real and imaginary part. Then this is it's always the Fourier transform of something, and that something is x of t times e to the minus sigma t. So this real part of s represents an exponential, a real exponential that I've multiplied by x. Okay, so let me emphasize what this is with some graphs here. So if we have some signal, x of t, maybe it's like, okay, and I'm kind of trying to indicate that it doesn't go away. It gets bigger and bigger with time. It goes on for infinity, getting bigger and bigger. Now, this would be one of those cases where such a signal, a Fourier transform wouldn't be able to handle this, right? Because I'm implying that it has infinite energy. It's unstable in some sense. Okay, now the Laplace transform is saying, well, if maybe the Fourier transform can't handle this, but if we first multiply it by an exponential function like this, that is our e to the minus sigma t. So we pick sigma to taper this thing down. Then the product here would be something like this. So who knows? Something like that. I'm trying to do this multiplication. And assuming sigma was large enough, it might be able to control the tail of this signal, right? And make it have finite energy. Okay? So that's one way of using a Fourier analysis on a signal that otherwise you couldn't. Let's taper it down with an exponential and then do a Fourier analysis. And that's exactly what Laplace transform is doing, except it's doing it sort of for all possible sigmas at once. I mean, that's the way you might think of it. So so we have here, as we see, if sigma is large enough, the Fourier transform might converge. Which would mean finite energy, right? Well, they may not exactly mean the same thing, but they're close to meaning the same thing. And for our purposes, we only want to use Fourier transform on finite energy signals. Okay. Now, you also notice that if sigma is too either too large or too small, this can cause divergence. Okay, so why would I say it can cause divergence? I mean, obviously in the above picture, if sigma is too small, then you don't get any tapering off. and you're stuck with x, which does not converge. Okay, so we can see how sigma too small might be a problem. What if x of t by itself already converged in the Fourier transform? Then does that mean the Laplace transform will converge for all sigma? No, because you can think sigma can be negative, right? I can take something that does converge, but then I can put e to the I can use a negative sigma. That would be an increasing exponential, and I can cause it to no longer converge. All right. So that's what I mean by sigma too small. Why do I say sigma too large? Sigma too large means this decays very quickly. How could that be a problem? What? Absolutely. Absolutely. The signals can go both directions, right? I've drawn it like it starts at some point in time, but signals can go, it could go off this direction like sync forever as well. So then if sigma is too large, it's causing this tail to potentially blow up. Okay, the left side. So think of signals that go off to the left. Okay, so basically what we said here is that we have some, in this S space, complex plane. Here's the real part of S. Here's the imaginary part of S. Okay. What we have is, we've identified some things here. For example, this slice of it, the imaginary axis, this is the Fourier transform. Okay, now remember, think about it. As you move along that slice, the value of this function is complex. So just take the values along this line, and that's your complex valued Fourier transform. Okay, but we also have that every vertical line has a similar interpretation. So another line over here that's at the line where the real part is sigma naught, this is exactly the Fourier transform of not x, but x of t e to the negative sigma naught t. So it's just a new signal, and that's the Fourier transform of that new one. Okay. So therefore, as we've said, the real part of S equals sigma. This is the exponential decay. You can interpret the real part as the exponential decay, and the imaginary part is the frequency. Okay, so that's how we can interpret this Laplace transform. Now, notice also notice how redundant this Laplace transform is. Why do I say it's redundant? I mean, we start with the signal. If we transform it, we just need to keep enough information to be able to transform it back. So why would I say this is redundant? Yeah, exactly, because any one of these lines in the region of convergence is enough to get the x of t back. But when I say, I should qualify what I say here. I say that's the Fourier transform. I should say if in the region of convergence. So these only can be interpreted as Fourier transforms if in ROC. Okay, if they're not in the region of convergence, don't interpret them as a Fourier transform. Okay, but anyway, any vertical line in the region of convergence is enough to get back x of t. All the rest are just extra things, no extra information, just new Fourier transforms of different versions of that same signal. Okay. All right, so I have a MATLAB demo here. I'm going to let's look at the example, Laplace transform. Let's do the Laplace transform of rect of t. Okay, we can calculate this out quite easily. X of s equals the integral of course, rect e to the minus st, which is an integral from negative half to half of this, which equals 1 over s times the endpoints subtracted from each other. So e to the, I guess it's minus s over 2 minus e to the s over 2. Is this correct? It looks correct. For some reason, when I had it in my notes, I had the negative in the other exponent, but this looks correct, right? Okay, so let's try to visualize. First of all, we should also say, what's the region of convergence here? And this is a good example for region of convergence because any ideas for which s does this converge? Does the integral ever have a problem for some s? I mean, no, it doesn't. I mean, we do have a divide by 0, but that's not really a problem with the integral. That's a problem with my formula. Because if we plug in s equals 0, we just get 1. So I could write this parametrically. It's this, except when s equals 0, it's 1. However, the limits are going to match up, so I won't bother with that. Okay, so that's not a problem. Really, there is no problem according to this integral, and we can see why. Whenever you have a finite duration, so this is all s are in the region of convergence. Okay, the whole complex plane. ROC equals complex plane. Okay, but this is always going to be true because rect, if we have finite duration, rect is a finite duration signal. There's no so if we look at rect here, if you multiply this by any exponential function, because it doesn't have tails, you'll never have a convergence issue. Take any exponential function, no matter how big, multiply the two, integrate, no problem, because it ends at a certain time, starts at a certain time. So in general, finite duration signals will always lead to this result, that the ROC is the complex plane. I'm going to use a different color. Okay, so the ROC will always be the complex plane if it's finite duration. All right, that's something we'll see. So let's graph this because, like I said, I mean, this Laplace transform I expect is still kind of this mysterious object. It's some complex function over complex argument. So what I've done here is just calculated that. I should correct the minus signs, though. It's minus here and plus here. That's not going to change much of the look of this thing. Okay, so all I've done here is I do a three-dimensional plot of h of s. That's going to be the Laplace transform. It's just the formula we just wrote out. And I'm going to graph it. Okay, maybe I'll do this. Yeah, that looks kind of funny. All right, so he saw me practicing this. So he's like, I saw that. You want to tell us about it? Okay, so what I've done here is, because we have a two-dimensional value over a two-dimensional space. So this is the imaginary. This is the real axis here, and this is the imaginary axis. Notice they're on a different scale. And so what I have. So here's how we normally look at it. Right, we look down, and we're seeing real part, imaginary part. And we have now a two-dimensional function. What I'm doing is the magnitude of the Laplace transform, I'm using the height to indicate the magnitude, and I'm using the color to indicate the phase. Okay, so the color here, we have a color bar. The phase goes between pi and negative pi here, and that's just what these colors are. Now, when you see these sharp changes in phase, they're not really sharp changes in phase. You're just wrapping around from, plus pi and minus pi are the same in phase. right? So it's just that the phase went past pi and went around to negative pi, and so it looked like a sharp line, but it's really continuous. All right. So let's take some good look at this thing. So this is an interesting Laplace transform. I mentioned that the region of convergence is everywhere. You don't have any convergence issues. And what's kind of cool, you see all those little ripples and stuff. What's fun is to look at it from this direction. Okay, so we're seeing the lower part of that is exactly in the middle. What's the middle of this thing? What's this direction? Sinc. And why is that? So this here, the center of this is exactly the imaginary axis. And what we said is the Fourier transform lives on the imaginary axis of the Laplace transform. So as I turn it and we get a good profile of that exact line down the middle, we should see sinc, because that's the Fourier transform of rect. Right? Now we actually are seeing absolute value of sinc. Sinc would go below 0 here and above and below. We're seeing the absolute value because we're taking the magnitude. Of course, negative just becomes a phase of pi. So if we looked carefully at the phase, we'd see the phase should change by pi every time it crossed over. Okay, but you see sinc there. So I hope that kind of gets the point across of what we mean by the Fourier transform is this slice of the Laplace transform. Every other slice is the Fourier transform of some rect times the exponential. Okay, which doesn't, by the way, have any zero crossings, as you can see. Okay, so keep that in your head. If you want, remind yourself of this every once in a while so you have some visualization of Laplace transform. Now what we need are we need a better understanding of this region of convergence. And we'll learn some cool things. First of all, they're always vertical strips. So what that means is, for example, you can have something like here. I'll highlight a region of convergence. Here's the real part again of S, and an imaginary part this way. And if I'm just trying to show you where the region of convergence might be, it's always going to be you'll have boundaries that are vertical, and the region of convergence will be contained in some vertical. It'll be some vertical strip of the complex plane. Okay, so now the endpoints don't have to occur. So these are, say, left and right boundaries are both optional. In other words, I'm still calling it a vertical strip, even if there's no right boundary, and it just has a left boundary and goes off forever to the right. This is, in some sense, is still a vertical strip. If it has no boundaries, it's the whole complex plane, fine, that's still a vertical strip. Okay? But those are all the shapes it can take, so it's actually very simple. So really expressing the region of convergence is just a matter of expressing which real values of S make it converge. And that kind of makes sense in our Fourier transform interpretation. We're saying which exponentials will make the Fourier transform exist. Okay, the real part of S is the exponential that you multiply by it. Okay, so it's very straightforward in that way. Now, we understand something about stability as well. By stability, I mean, so far we're just talking about the Laplace transform of a signal. But let's say that signal is the impulse response. Let h of t be the impulse response of a system. Because really, that's going to be what we use this Laplace transform for. Okay, so this is the impulse response of a system. The system is stable if the ROC of H of S, so the Laplace transform's region of convergence, contains the imaginary axis in its interior. So I'll mention the importance of that momentarily. So what does it mean to interior? So really what we're saying is if the Fourier transform exists, then it's stable. But we know that's not quite true. Okay, but it should be somewhat related, right? I mean, okay, if the Fourier transform exists, then the impulse response has finite energy. We know that. And this statement here is I'm saying if H of S contains the imaginary axis if it contains the imaginary axis and we leave off this in the interior part, then we know that the Fourier transform exists. Okay. If we add this thing here, saying in its interior, that just means not on the boundary. Okay. Then we can conclude that it's actually going to be a stable. It's going to be a stable system. Okay. So it's almost the same. I mean, if you look at it, the criterion according to the Laplace transform, it's almost the same as saying the Fourier transform exists, but it's just slightly stronger. It's saying not only does the Fourier transform in the region of convergence, meaning the imaginary axis, right, but also it's actually not a boundary point of the region of convergence. So the boundaries are strictly to the right and to the left of the imaginary axis. Okay, then it's a stable system. And the other direction is true as well. If it's stable, then it will be in the interior. Okay. So I'd like to illustrate an example just to show you this weird intricacy where the Fourier transform, the imaginary axis can be on the boundary of the region of convergence. Okay, and look at a signal that's dear to all of us, sinc of t. Okay, x of t is sinc of t. Now, let's look at the Laplace transform of this. Okay, so the Laplace transform, well, let's just first say what is the region of convergence for this Laplace transform. Any ideas? For which real parts of S will this converge? Okay, yes, it contains, so you're saying that the real part of S equals 0 is in the region of convergence. And what else? What? And why would you say nothing else? Yes. Exactly. So you multiply any exponential there. Make it positive or negative. One side is going to be growing, right? And as was just mentioned, sinc falls off as 1 over t. And exponentials will beat polynomials. So no matter how slow that exponential is growing, eventually it's going to dominate the 1 over t term. And your sinc, so sinc times an exponential, will blow up in one direction, no matter how small that exponential is. Okay? So what that means is this is the region of convergence. It's just that. Nothing else. The narrowest strip you can imagine. All right? Now, what do we know about... So this... Yep. So... There are? Yes, exactly. Yeah, if you have like x of t equals t squared, yep, it's not going to converge no matter what. So you don't have to... Yeah, the region of convergence can be empty as well. Okay, so I guess that is a smaller region of convergence than this. All right. Now, what do we know about sync? If sync was the impulse response of a system, in other words, an ideal low-pass filter, is it stable? So this was our example that we did when we talked about stability. It's not a stable system. And we then used that to come up with a way of showing that stability can be checked by integrating the absolute value of the impulse response. And the absolute value of sync does not converge. Okay, so it would not be stable. So my point here in this example is we know, I should have said H, just so that you think this is a system's impulse response. We know that this is not stable because we worked it out before. So this is a good way of seeing why this condition of the interior is important. You see here, yes, the imaginary axis is in the region of convergence, but it's not in the interior. Okay, so that's why we didn't break our rule up above. In fact, this has a very uninteresting Laplace transform, since the region of convergence is just the imaginary axis, which means the entire Laplace transform is just the Fourier transform. The Laplace transform is not going to help us do anything when it comes to sync. So even though we love sync so much, when we are dealing with Laplace transforms and system stability, we're not going to be talking about sync anymore for this last week. Okay. Now, we have some, let's give some names to different types of signals because they're going to correlate with the region of convergence. Okay, so we have something called a right-sided signal. And this means, I'll draw a picture. All right, so it means that at some point in time, who knows what that point is, the signal starts and maybe goes on forever to the left. I'll use blue so we don't confuse it with the axis. So maybe something like that, ... right-sided, okay? But actually, mathematically, to be right-sided, the important feature is not that it actually goes on forever to the right. That's sort of implied by saying that, but that's not required. What's required is that it doesn't go on to the left. All right? So mathematically, we say it's right-sided if there exists a t such that x of t equals 0 for all t less than that value. Okay, so there's some starting point to the left. All right, so that's what we call right-sided. And the implication in the Laplace transform is that the region of convergence has no right boundary. Okay, so it's either nothing, it could be nothing, or what we mean here is if sigma, if sigma, yeah, let's see. If real part of S equals sigma is in the ROC, then then any sigma greater than, then for any sigma prime greater than sigma, then it's also in the ROC. Yeah. So we're just saying if it converges for some points, I could converge nowhere, but if it converges somewhere, then it's also going to converge for every greater value of sigma. Is it clear why that happens? Can someone give an explanation? Why would this be true? Yes? Exactly. So, yeah, because by increasing, if we already got it to converge for some exponential, by increasing sigma, yeah, it tapers off faster to the right. And that's the only part we have to worry about for convergence with this type of signal. Now, it's true, t could be negative, in which case you're growing the left side of your signal, but it doesn't, it has a finite duration in that direction, so it's never going to cause convergence issues. You can bound what happens based on cap t. Okay, so and of course then we have the opposite, left-sided, which has the opposite definition. Signal, which is that there exists some t such that x of t equals 0 for all t greater than that value, right? This then is the opposite here, has no left boundary. Okay, and then we've got a couple more. Let me just put numbers here so we don't get lost. Now we have something that's called two-sided. And this is, what do you think a two-sided signal looks like? Yeah, it should be. If it meant both left-sided and right-sided, then it would be finite duration. It's unfortunate naming. So, yes. It does not mean it's both left-sided and right-sided mathematically, right? It means that what kind of the name implies, it kind of goes on in both directions and is not bounded. Technically, I would say technically it means nothing, okay? Any signal you could say is a two-sided signal, all right? But the implication if you say something is two-sided, it would be that it's not left-sided and it's not right-sided. It doesn't have a bounds in either direction would be the implication. But I'm not even going to give it a mathematical definition because I think mathematically any signal could be called two-sided. It's really an interesting name. But then we have finite duration, and this is useful. Okay, and we already talked about finite duration. Mathematically, this is both left-sided and right-sided. Okay, and it's what you expect. It's like rect. Okay. Now this, you can say some things about the region of convergence for this thing. What do we know about the region of convergence for finite duration? Yeah, or nothing. Could be nothing. Well, it could be nothing, but by using something with vertical asymptotes. Okay. Yeah, let's just say, I'm going to just say has no left or right boundaries. In all of these cases, I guess a caveat to all of these, or all of them, there could be no region of convergence for any of these signals, okay? Because you can always take 1 over t or something, and you don't converge no matter what happens, right? So, but we're not really going to dwell on those cases. So, I could have put it as a note on each of these. It's either this or the region of convergence is empty. It's either this or the region of convergence is empty, and so forth, okay? But those cases where the region of convergence is empty, you'd spot that from once you looked at the signal. We're not really interested in those cases. So in other words, everywhere or nowhere, right? That's what happens in finite duration. Okay, yeah, just a note on this naming. The naming, it makes sense from a intuitive point of view, what you think it's supposed to mean. Right-sided, okay, it goes on to the right. Left side goes on the left. Two-sided goes on both directions. But unfortunately, that when you get precise and look at how it's defined, traditionally, it's not defined the way you expect it to mean. You expect right-sided to mean that it's not bounded to the right. That it doesn't have a finite time when it stops to the right. That's not what it's defined to mean. It's defined to mean that it does have one to the left. Okay, and that's useful because then that lets you know something about the region of convergence. All right. So what about causal? Suppose you have a system that is causal, and we want to look at the transfer function. I'm going to use that word again, transfer function, which by that I mean the transform of the impulse response. Okay? So in this case, before we were doing Fourier transforms, in this case now we're doing Laplace transforms. So I'm still going to call that the transfer function, the Laplace transform of the impulse response. So if a system is causal, what do we know about its transfer function? What do we know about the region of convergence at least? So causal means that that implies right-sided. It implies that the impulse response is right-sided, right? So causal is a particular right-sided signal, right? I mean, okay. So what we talked about what the impulse response of a causal system looks like. Let's remember what that is. Someone want to mention specifically what we've said in the past for LTI systems that are causal? What do we know about the impulse response? Yes, exactly. So h of t equals 0 for all t less than 0. That is what we know by causal, right? Okay, and that implies that it's right-sided, right? With a cap t equals 0. Okay, so causal is in some sense a stronger thing than right-sided. All right. So then that implies that something that's very worth remembering about the Laplace transform. If you have a causal system, and the reason I mention this is because we care about causal systems. If we're going to do anything in real time, it's always going to be a causal system. All right. So if your system is causal, then what do we know about the region of convergence of the Laplace transform? Has no right boundary. Okay, so for causal systems, the region of convergence is always to the left of some value, or nothing, or everything, but it's not going to have a right boundary. Okay, so that's a good to remember. Okay. So we're actually going to, there's a particular class of Laplace transforms that we're going to be mostly interested in. In fact, exclusively interested in for the duration of this class because we only have a few lectures. And that is rational Laplace transforms. Okay, rational just means the following. A rational function. So here's a rational function is a ratio of a polynomial, a numerator that's a polynomial, to a denominator that's a polynomial. Okay, so these are both polynomials. Okay, and we call this a rational function. You'll see why. We may or may not have time today, but we'll be able to see why this is so important and we care about this class of functions. For a lot of control theory, this is all you ever worry about. It's rational Laplace transforms. Okay, so, but of course, a polynomial can always be factored into a bunch of terms multiplied together. So you could write such a thing as like product of s minus some root. You take the roots of the numerator, all right? And let's call those s z1 here, s minus s z2 dot dot dot, and we have some roots of the denominator, sp1 s minus sp2 dot dot dot. Of course, the number of these terms is going to be equal to the order of your polynomial, right? So sometimes you say that the rational function has an order, and the order of the rational function is just the maximum of the two orders here, the numerator and denominator. Okay, so if we just think about what this function is now, thinking about s as complex valued, right? S and potentially the sz1, sz2, and so forth could all be complex valued. All right. Then polynomials are a little bit, different than you think of in real valued polynomials. I should mention, by the way, we would still call it a rational function if you had some constant c times it. Okay, so I should put a constant c there. Of course, that could just be part of the numerator, so I guess I don't need it. Yeah. Okay. So, but I would need it down here. So you'd have a constant times this factorization, right? Okay. So what's interesting then is to look at the magnitude and phase of these rational functions. So, by the way, the first example we looked at, let's go back up and see, is it rational? So we looked at this. Okay. And is this a rational Laplace transform? Yes. Right? Polynomial. Okay. And I think I mentioned to you that e to the t u of t was actually a function we care about. It shows up as the solution to differential equations often and so forth. Okay. So we basically were saying, let's just consider for now Laplace transforms of this form. Okay. Now, what happens is that means that the entire function is specified by a constant. I usually won't worry much about what that constant is. And these values, the SZs and the SPs here. And we call these, we have certain names for these things. The SPI are the poles, the poles. And the SZs are the zeros. And that's why I've used Z and P. So basically, a rational function has zeros and poles and a constant, and that defines the whole function. Okay. So we're actually going to have let's look for a moment at what the magnitude of such a thing is. The magnitude is going to be the magnitude of C time, and remember, magnitudes multiply, so it's the magnitudes of each of these terms multiplied together. Whoops, Z1, Z2. So really, what we should try to understand is what's the magnitude of one of these things. So this, for the zeros, we have, if we take one of the zeros, okay, this is just a vector. So let's suppose that we put the zeros and the poles on our Laplace transform plot. Okay, we have real part of S. We have imaginary part of S. And remember, we have a Laplace transform, which is some function on this space, right? But we can, on the top of this, let's just put X's for poles and zeros for zeros. Right? We'll put little O's. Okay. Now, what's nice is, given that it's a rational function, that picture right there expresses the entire function up to the constant. Okay. So aside from the constant C, the location of the poles and zeros expresses the entire function. Let's see how we would interpret how the function behaves given the locations of the poles and zeros. Now we see that the magnitude... Okay, either sit down or you guys can go play outside, okay? Out in the hall. Okay. So if you want to... So S is our variable. It's our complex variable here, right? So if we want to understand what's the magnitude of the Laplace transform at a particular value of S, let's say that value of S, what we have are the vectors from all of the zeros. This is the length of the vector. So what that means is, let's say this one here was SZ1, Z1, and this one here is SZ2, and this is SP1, SP2, SP3. Okay? Then the magnitude of this first term is simply take this line here. That vector is S minus SZ1, right? And that is exactly what this magnitude is. So you would take your distance to the zeros, and you'd multiply them. And you take your distance to the poles, and what do you do with those distances? Divide. So the magnitude of the Laplace transform at any one point is the product of the distances to the zeros divided by the product of the distances to the poles. So very easy geometrically to kind of interpret that. What does that mean if you're near one of the zeros? What will the magnitude be? It'll be very small. Okay? If you're near one of the poles, it'll be very large. That term will dominate the rest, right? If you're very close, you'll be dividing by a very small number. So already from the zero pole plot, you can, in your mind, imagine a very interesting contour. These poles are like tent poles. Okay, they're like poles going up in the air, and you pull a tent taut over these poles, and then the zeros are like stakes. You go drive stakes into the ground where the zeros are. Okay, because the value of the Laplace transform at those zeros has to equal 0. Okay, so the magnitude of this Laplace transform is staked to the ground there and goes to infinity here at these three spots. Okay, so we have an easy way to kind of interpret magnitude by looking at the pole zero locations. Okay, now what about phase? Okay, the phase, again, we would have phase of C, so some constant phase from the constant, plus the sum over the zeros of the phase of S minus SZI, right? Minus the sum over the poles of the phase of S minus SPI. So what we mean by that is we take these vectors, these lines here, but what we do, rather than looking at their distance, we look at their angles, right? Because the phase of S minus SZI, this line here is S minus SZI, this one, right? SZ1, S minus SZ1. And the angle of that number is 0 because it's just horizontal. But let's take the next one. Let's look at S minus SZ2, this red vector. Its phase angle is exactly this thing, right? I'll say this is the phase of S minus SZ1. Okay, is that angle there. So you can pull out of the pole zero plot the phase of the Laplace transform at any one point by just looking at all the angles to the poles and zeros. Again, if you were trying to do this quickly and just get some intuition of what happens to the phase, then if you look at some values of S very near one of the poles or zeros, and you consider how the phase changes as you move through the Laplace transform, that's often what you want to know. How is the phase changing if I move along here and I'm right next to one of the poles? Well, the angle with the other poles and zeros is not going to change much. But the angle with the one you're close to will change a lot. Okay, so that will kind of dictate how much the phase is changing. Okay, so we have this idea of poles and zeros. we have something else very nice with poles and zeros that makes this whole business with the Laplace transform actually quite easy. So once you get used to these little rules, everything we do with the Laplace transform is actually pretty easy. So for rational Laplace transforms, the region of convergence, the boundaries of the region of convergence are just those points. Probably someone can guess where they are, because there are certain points in a rational function. The infinities, you know, that means that something didn't converge. So the boundaries of the ROC are the poles. They're always at a pole. Okay, so what that means is if we take my picture right up here, I'm going to redraw it because there's too many colors up there. So here's the S-plane. If we have some poles and zeros, I'll draw some new ones. 0, 0, pole, pole. You'll notice I always kind of draw these in pairs. That's for real systems, they always come in pairs. Okay, or they come on the real axis. So if I have something like this, let me do this. Bunch of poles and zeros. There are several possible regions of convergence for this rational Laplace transform, but not as many as you might think. Okay, so we can list out what the possible regions of convergence are. One possible region of convergence is everything to the left of the leftmost pole. So this would be one. Take these are the same real value. So everything over here, that's one possible region of convergence. Okay. There's another possible region of convergence that is between these two boundaries. Okay. There's another one that is, again, I intend for these to have the same real value. So there's another one that's between these two. And then finally, there's one that's to the right of the rightmost pole. Okay. So what this means is there are 4 possible impulse responses, okay, that would all give the same rational Laplace transform, but they would give different regions of convergence. Actually, let's talk about these four impulse responses. The one corresponding with the blue region of convergence. What can we say about it based on this plot here? Yeah, you're saying it's the one you can get from the inverse Fourier transform, which means it has a Fourier transform, right? Yes, so the Fourier transform converges. What else do we know about it? So, anything else? Yeah, oh, you're saying finite duration? Two-sided. Because finite duration would mean, so it's not finite duration. We know it's not finite duration, because then the region of convergence would have been everywhere. So we specifically know it's not left-sided, it's not right-sided. We can say it's two-sided, and even though that statement is vacuous, it implies what we mean it to imply. Okay, so now what about the purple then? Purple, many things are the same, right? It's not left or right-sided. I mean, it's two-sided, but it does not have a Fourier transform. Okay. In fact, we can even tell that, considering where it converges, you needed to have exponentials that were growing in order to make the Fourier transform converge. I'm just looking at the real values of S that caused convergence. Therefore, the signal probably tapers. It must taper this way. Okay, it must grow to the left, and that's why we needed negative values of sigma to get it to converge. All right. Now, the green one is left-sided, and the yellow one is right-sided, which means the yellow one might be causal. Okay. In fact, it'll turn out for these rational Laplace transforms that if it is right-sided, it'll be causal. Okay. So this yellow one is causal, but is it stable? No, it doesn't have a Fourier transform, and it's not stable, right? So actually, that means for these, so again, I hope you agree this turns out to be very simple. For a rational Laplace transform, we have an easy check to see whether or not it could correspond to a causal stable system. Okay, so just by looking at poles and zeros, so you can quickly check whether a rational Laplace transform could be causal and stable together, right? Could be both causal and stable. Because really, we're going to care about that. We're going to want systems that are causal to be stable. Okay. So what would that check be? How would we check whether it could be causal and stable? Yes, Victor? Yeah, poles you mean, but yes. All poles, let's say, are in the left half plane, which is exactly what you're saying. So I'll say real part's negative. If you only remember one thing about the Laplace transform later in your life as you're asked about it, remember this. Because this is really what, this is what comes off people's tongues when they talk about stability in the Laplace transform. Oh yeah, the poles have to be in the left half plane. Now, we're talking about stable systems. Of course, causal systems. Of course, you could have a non-causal, if you have a non-causal system. So you're doing something not real time, I guess. Then yes, it can be stable and not have all the poles on the left half plane, right? But because we usually care about, controlling some rocket or something that's happening in real time, we're building causal systems, and then we only care about this one region of convergence, the one over here to the right. And for it to be stable, the poles have to be on the left. Okay. So the reason I say this, we check whether it could be, is because I haven't yet said whether the system is causal. Okay. But if in your actual problem you know that it's causal, then fine. Then this is the condition for stability. All right. It's a very simple condition, right? Okay. Let me introduce the Z transform, and then we can end. All right. So the Z transform is for discrete time signals. So when we had the Fourier, when we were doing Fourier transform, there wasn't that much difference between continuous time and discrete time. There were some key differences. The discrete time Fourier transform is always periodic. The continuous time Fourier transform is not. Okay, so nice things to remember. But here we name a whole new transform for discrete time. You'll see they're very related, and that's why I can introduce it quite quickly. So here we say x of z equals a sum x of n z to the negative n. Okay, so the first thing we're going to want to do, and of course now z is complex. All right, so just like the Laplace transform, we have now some complex plane of z values. Again, it won't converge for all z. Okay, so how does this relate to the Laplace transform? Well, the Fourier transform. How does this relate to the Fourier transform? Well, let z represent z in polar coordinates, right? So z equals a e to the I 2 pi f. Okay, so there we go. Any complex number could be represented this way as a magnitude and phase. Then we substitute that in for z, and we would have then x of this a e to the I 2 pi f equals xn a to the negative n e to the negative I 2 pi fn. And that is the Fourier transform of xn times a to the negative n. Okay, so we see again that this is just a generalization of the Fourier transform, where we've again just multiplied by an exponential term and taken a Fourier transform. So really, it's the same thing. The only difference is that we don't write it as a e to the negative sn. We could have written that, and we could have said, so the relationship to the Laplace transform is that z equals e to the s. Okay, if you let z equal e to the s, then you see just plugging that in here, we would have e to the negative sn. It would be just like the Laplace transform. So you might say, well, what's the point of changing the way we represent a complex number to come up with a new transform? I think the reason is the following. Because of aliasing, if you left it as e to the negative sn, you would get a Laplace transform that was periodic. In other words, every time you increased the value of s every time you increased the imaginary part of s by 2 pi, you would get back to the same Laplace transform value. And so if you just change it to this notation, it kind of wraps the periodicity into one cycle. So really, fundamentally, there's not much difference between these. However, when you actually go to use the z transform, this change of variables, calling it z rather than e to the s, means that you have some new properties. For example, regions of convergence are not vertical strips anymore. They're rings. Okay? So what happens is you have the z domain here. You have a real part of z, imaginary part of z, and now you've got boundaries of your region of convergence that are circles. And maybe you've got two boundaries, or maybe one of the boundaries doesn't exist. Let's draw that better. And the region of convergence is between two boundaries like this. Okay, so it's a different region of convergence. Before it was a vertical strip, now it's this. Again, you can see exactly why that's the case, because the magnitude of z is what I'm calling a here. That's the magnitude of z. And you see that we're talking about Fourier transforms of your signal times some exponential, but now that exponential is characterized by the magnitude of z, not the real part. In the Laplace transform, it was the real part of s that caused the exponential. In the z transform, it's the magnitude of z. So this here, magnitude of z, right, equals a. So, of course, the magnitude of z is what's going to determine whether it converges or not here. Okay? The best thing to remember is think of the S-plane. So the S-plane has been wrapped around. So imagine that you took your S-plane with it, which had vertical regions of convergence like this. Okay, and you had things like this as a region of convergence. And imagine that you take the imaginary axis and you bend it into a big circle. Okay, and you take every vertical line and bend it into a big circle. And so the negative infinity real values, where did they go? They went to the center of your circle. And the positive infinity real values, they got bent around to all the infinities of the z-plane correspond to the positive real infinity. So you just took all of space and you squished it into a big circle. Okay, and what that means is where did this imaginary axis go? When you did this transfer, this is just doing this transformation, z equals e to the s. Where did the imaginary axis go? It became the unit circle. Okay, so what that means is the Fourier transform, the discrete time Fourier transform, is the unit circle of the z transform. Okay, we'll talk more about this next time.